right. Good. People are showing up. Good. All right. And let me take a look at the schedule. So we're down here, and we have guests next week. I don't have the next quiz up yet, but it's going to be another week before it's due, so that's fine. Artyom used to be a student here. He's very good. He gives a lot of talks about threat actor research, tracking down who's sending out various forms of attacks and tracking down their command and control centers and stuff. So that'll be good. And other things are coming up. There is another purple competition this Saturday. It's worth extra credit for anybody that comes, and should be good. Last time it went pretty well. And this time I just have to have a script to automate putting up the box that people put up manually last week. And then we'll start doing Drupal-Geddon attacks and picking them up with Splunk. All right. And I guess those are the immediate things coming up. Let me take a look at the news. All right. I thought this one was pretty interesting. That's kind of interesting too. Possibly that also. Well, that might be it. So Microsoft has come up with Internet Explorer or Edge based on Chromium. And what I thought is very interesting is they showed all the Google stuff they removed, which is really a lot. And this is why I quit using Chrome. Chrome is all full of extra Google junk that tricks you into logging in and synchronizing with other devices and everything else. You can see Google has just started throwing everything but the kitchen sink into their browser, which is, what Firefox did. I mean, their browser's so big it actually wouldn't fit in the memory on 32-bit machines, and then they had to cut it back and stuff. Anyway, so I haven't tried the new Microsoft browser, but people are saying it's pretty good. So this is another startup. There's Airbnb and Uber, both of which started doing something that is technically illegal, and they just sort of slammed it in and dared people to do something about it. And Kobo is doing the same thing. It's a local startup, and this idea is you will now rent out rooms in your house for business, so people can use them as offices. But their idea of promoting this was to put out a flyer like this that looked like it had just been written with a Sharpie, and to stick this in everybody's mailbox in a neighborhood, and then claim that they were in stealth mode and they couldn't answer any questions and no one's supposed to know. But some of the people they gave it to were like on the Board of Supervisors in the Housing Association, in the local government, which is exactly the people that passes zoning rules against this. So they're getting all angry and bent out of shape and saying, you just like Airbnb, you have like a residential district, and then you have some guy renting it out to someone new every day and a whole bunch of strangers wandering through, and everybody gets nervous. So they're probably going to punish these guys and limit them like those other things. Anyway, this came up just yesterday in class. I was surprised. Someone asking about seizure, asset forfeiture, and it came up in the news. For about the last 10 years, laws have been passed that permit the police to just grab stuff from people who are accused of crimes without ever really proving they did anything. They just say, you look like you probably bought that with your drug money. And now some people are finally pushing back on this. It is a very strange situation in the law where you have your property taken, you can't get it back, and yet you were not convicted of a crime. It's like punishment without conviction, and they're finally getting some pushback. People, it's often expensive cars. They took couple people's cars, and they're actually getting lawyers and making some progress at getting their stuff back. So maybe there will begin to be some limits here, but it's all extremely unclear where the limit is. And in the same thing here, free speech seems to have had its heyday and died off again. I see a comment coming in. These assets may be used to pay confidential informants. Oh, I didn't know that. That's even more disturbing. So I go to you and I say, if you rat out this guy, I'll give you his car. Yeah, that does seem like a questionable thing to do. So anyway, everyone's pretty much given up on free speech. Everyone's decided that we have to censor political speech. It's much more extreme in Britain than it is here. And so now they are passing a law in Britain. This legislation says that everyone who permits someone else to post content is now required to remove the harmful content, but they won't define what harmful content is. So it basically means you're constantly breaking the law no matter what you do. I'm just looking at it. I don't understand how anybody can have a search engine or a blog with comments, YouTube comments, or anything with this. So people are screaming and yelling and deciding what to do. I must say, everyone's yelling at Zuckerberg and saying he was just self-serving, but I think what Zuckerberg said is correct, that if you're going to have to censor the internet, you have to write clear rules. So it is possible for us to do it and to prove that we've done it. You can't just have some vague rule where we don't know what we're allowed to put up and what we're not allowed to put up. But of course, it turns out to be extremely difficult to define exactly what the forbidden speech is. And yet politicians want to be perceived as having done something, so they're tempted to just pass some vague law that doesn't mean anything and leave everybody hanging. That's probably what's going to happen. Anyway, there's spyware from Android that has now found its way to iOS, which is interesting. And this is a surveillance tool with legitimate Apple developer certificates. So apparently they bribed or stolen a legitimate certificate, and this may be interesting to see. Anyway, I'm not quite sure how you get that stuff installed, but we'll play with more of that in the mobile device hacking class, which has been almost all Android, but I'll try and have some coverage of iOS in it. Anyway, we're down to RSA. So let's take a look at that. That is, I don't need this stuff. All right, too many things going on. All right. That should do it. All right. And I'm going to need Cahoots later. Let me bring them up. Wait a minute, I might not have the Cahoots again. I think I forgot to put them up. I think I wrote them and forgot to post them again. Yep. All right. We'll see if there's a chance to put them up later or not. Might have a chance. Anyway, so, all right, so let's talk about RSA. I have some different descriptions of it here than what's in the book that certainly helped me understand it better. It takes a lot of passes to get RSA right, and this book is much more clear than any other book I've seen. So this is the fundamental concept you need, the group Zn star. In the simple case, which is the only one I used to understand, you use n equal to a prime number. And in that case, this group is so simple as to actually fool me into thinking I understand it when I don't. If it's a prime number, then it's just all the numbers up to p minus 1 except 0. That's the group. So Z star 5 contains 1, 2, 3, and 4. And the reason for this will become clear. This means all those numbers are generators of the group. Well, I guess 1 can't be. Anyway, we'll get here. So here's the game. Z star 4 contains only 1 and 3, though, because 2 has no inverse. If you're going to use an n that is not a prime number, then there are some numbers that are factors of that number, and those numbers are forbidden because you can never make it to 1. And we'll see that here. So consider n equals 10. Here's a circle with 10 possibilities, and we're going to do 0, multiples of 0. So you take 0 times 1, 0 times 2, 0 times 3, you always hit 0. But if you take multiples of 1, 1 times 1, 1 times 2, 1 times 3, you generate everything all the way around. So 1 has an inverse. There is a number that will eventually get you back to 1. 0 has no inverse. There's nothing you can multiply it by that will get you to 1, so it's not in the group, because you have to have inverses for anything in the group. So here's multiples of 2. The problem with anything that is a factor of the modulus is that 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4. There's nothing you can multiply 2 by that will get back to 1. And in fact, the set of all the numbers you can reach by multiplying 2 by something is only a part of the group. You never hit all the numbers, or a part of the possibilities. So 2 is not in the group. 3, however, is, because 3 does not divide 10 evenly. So if you go 3 times 1, 3 times 2, 3 times 3, you go around and eventually hit all the numbers. And here's 4. 4 is a multiple of 2. So if you take 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 2 again. And so you never hit 1. And the same thing with 5. You're just going to flip between 0 and 5 because 5 is a multiple divider of 10. And the same thing with 6, but 7 does not divide into 10. So if you take 7 times 1, 7 times 2, and so on, you generate all the numbers in the group, including 1. And here's 8 is not in the group, but 9 is in the group. And that's why even though there are 10 numbers from 0 to 9, there are only 4 numbers in the group, because you have to have, for things to be in the group, they have to have an inverse. And only those numbers have inverse. 1 is its own inverse, and 3, 7, and 9 have other numbers up there that are inverses. All right, this is also called being co-prime with 10. If you are not, you have to be a number which does not share any prime factors with the n, or you will not be able to hit all the numbers and you won't hit 1. And this means that if you have n numbers in the modulus, you cannot use all those n numbers for RSA. The only ones you can use are the ones in the group, and the number of numbers in the group is Euler's totient. This is the phi of n I've seen before, and again, I never understood it as well as I did when this book explained it. So the point here is, this is the number of elements in the group. So if n is 10, which is 2 times 5, Euler's totient is 1 times 4. It's p minus 1 times q minus 1. This tells you there are 4 elements in the group when there are 10 elements around the ring. And those are the only ones you can actually use, because you have to be, remember we did this before at the beginning of the class with modular math, you're going to take a number to a power, which is hopping around the circle, and then you want to take it to another power to decrypt it. So you need to have an encryption key, which scrambles data, and a decryption key, which undoes what the encryption key did. And so here's the trapdoor permutation. N is the modulus, the product of 2 primes, E is the public exponent, and in practice, everybody just uses the same number, 65537. And your public key is just N and E. And nothing about that is secret. The private key is secret, which is P, and a whole series of other numbers that can be derived from P. So you encrypt by taking the plaintext message X to the E mod N. And you decrypt by taking the ciphertext to the D mod N. And the reason it works is because E and D combine to be a functional equivalent of 1 and undo each other's work. That's why you have to have only be using elements that have inverses. And here's E, D has to be 1 mod phi. And phi is Euler's totient. And so if you have y to the d mod n is the ciphertext, if you take y is x to the e, so this is x to the ed, and ed is 1, so you get back to your original plain text. That's the miracle of it. And I did a couple examples which made it much more clear to me. In fact, I got them wrong and had to repair them a few times. So if n equals 10, then I have a group with only 4 values, so let's encrypt a plain text of 3. So I can take the powers of 3. 3 to the 1 is 3, 3 to the 2 is 9, 3 cubed is 27, so that's twice all around and a 7 more. 3 to the 4th is 81, that's 8 times around and 1, that gets me back to 1. So 4 is the inverse of 3. All right, and so here's that chart. 3 to the 4th is 1, 3 to the 5th is 3 again, and you just hop around the elements of the group. So 3 is a generator of the group as all, and so if you keep taking 3 to different powers, you will eventually hit all the elements. So you encrypt by raising x to a power, and you decrypt by raising it to another power. So phi is 4, because I have 10, which is 2 times 5, and phi is p minus 1 minus q minus 1 times q minus 1, which is 1 times 4. And here's how you find d, which is kind of painful. You choose e, and I'm choosing an e of 3, and then you just try multiplying it by various numbers. So 3 times 1, 3 times 2, 3 times 3, and you take it mod 4, not mod n, but mod phi, because we're just hopping around the phi elements we can actually use of the circle, not all possible numbers on the circle. We're hopping around among these numbers, 1, 3, 7, and 9. So it turns out that the inverse of 4 is 3. Inverse of 3, rather, is 3. It's its own inverse. So the encryption key is 3, and the decryption key is 3. And so now if we encrypt a message, like say 3, we give it a 3 as a message, and we encrypt it by taking 3 cubed mod 10, which is 27, and gives us 7. 7 is the ciphertext. And to decrypt it, we take the 7 to the third power, because that's the decryption key, and that's 343 mod 10, and you get 3. So that's about the simplest case I could possibly make with a group with only 4 elements. And I tried a small step up, 14, 2 times 7, just to get it straight. So again, I'm going to use a plain text of 3. So I'm going to be raising it to various powers. So 3 to the 1 is 3, 3 to the 2 is 9, 3 to the cubed is 27, which is 2 times 14 minus 1, so it gets me to 13. 3 to the 4th is 81, that gets me around to 10. There's 3 to the 5th and 3 to the 6th. And so here they all are. This hops through the entire group. Z14 is 2 times 7. There are only 6 elements in the group. That's what phi is. And here are all the 6 elements. And if I start with 3 and raise it to powers, I generate the whole group. There they are, 1, 3, 5, 9, 11, and 13. That's the whole group. And if I want to find D, I can start, phi is here. It's P minus 1 times Q minus 1, which is 2 minus 1 times 7 minus 1. So there are 6 elements in the group. That's phi. And so what I need to do is find a number which will be 1 when multiplied by E, mod phi. So my encryption key is 5. So I take 5 times 1, 5 times 2, 5 times 3, and keep going until I get 1. And that turns out to be 5 times 5. So if I encrypt with 5, I decrypt with the same number again, 5. So if I encrypt a message of 5, then I encrypt by, I take a message of 3 and an encryption key of 5. So I take 3 to the 5th, mod 14, and that turns out to be 5. And then to decrypt it, I take 5 to the 5 mod 14, which gets me back down to 3. That's how it works. So the math is a little simple in principle, but the numbers get very large, and that turns out to be the huge problem with RSA encryption. It is very expensive. The numbers get extremely large, and the math gets very slow. So here's what you have to do to generate keys. You have to find some random prime numbers, P and Q, and they have to be pretty long. Then you have to calculate phi of n from P and Q, which is easy. Then you pick E. In practice, everybody just uses the same number for E, the same small number. And then you have to calculate D, which is the inverse of E. And that is a little annoying, but there is a known Euler's algorithm to make it relatively fast. So all these calculations are quite doable. The most expensive part is finding the prime number, because you just have to try random numbers until you hit a prime number, and the prime tests take a while. So you can do it easily in Python here, and it's kind of fun to see how slow it is. So let me see if I think I got it ready here. So if here, let me just blow this up. I've got this set from my demonstration earlier when I was getting ready for this lecture. So let me do this. All right. So if you import the library, which is here from crypto public key import RSA, a standard Python library, now you can generate a key. So if I generate a key, the original RSA was done with 512-bit keys. But this library is more modern than that, and it will not let you use anything below 1024, which is probably a good idea. There was an example in the textbook, I think last week, showing that there's a library that lets you make 31-bit keys, and it's kind of rude to let anybody do that because they're, of course, not worth anything. So 1024 is the smallest one it'll let me use. And took about 1 second to generate those keys. And watch how fast it goes up. 4096, or let's do 2048. 1, 2, about 2 seconds. If I do 4096, which is the current recommendation, that's how much it takes for 128 bits of safety. 1, 2, 3, 4, about 4 seconds. And if I move forward any, like 8192, 1, 2, 3, 4, it's actually so long it gets boring, and I think I have to wander off and do something else. It grows really fast. And this is not an outrageous number at all. We're already supposed to be using 4096. If you wanted any reasonable safety margin, you ought to be up here or even higher. And you can see how expensive it is to generate the key. Encryption and decryption are almost instant, but the key, is very slow to generate because it has to hunt for prime numbers, and the prime numbers are not very thick on the ground, and it has to keep trying random numbers till it finds one. So anyway, that's the game. You can easily encrypt and decrypt also. And here's how long it took to do the key generation. You can see how quickly it goes up. So the key generation, one of them took like a fifth of a second at 1024. 400 encryptions took 0.02 seconds, and 5 decryptions took 0.013 seconds. So the encryption is very fast. The decryption is a lot slower, like around 50 times slower, and the key generation is much, much slower again. That's how it generally works out when you do this with the typical values you use for RSA. So encrypting with RSA, the way it's actually done in practice, you could, in principle, encrypt your plain text directly with RSA, but in practice, nobody does it that way because RSA is so expensive. You don't want to have blocks of text running through RSA. Instead, you encrypt an AES key and send it there and then stream your data with AES. That's how HTTPS does it. That's how it's typically done. So normally, you only think about encrypting small messages with RSA. And so this is textbook RSA, which is what's in the first couple of projects where you have cartoons and using small numbers. You convert your plain text to ASCII, you put that in a number X, and then you just calculate Y is X to the E mod N. You're taking raw ASCII and just running it through the RSA algorithm to encrypt it. That is textbook RSA, and it's severely insecure, just like most textbook versions. One obvious thing, by the way, is that if you had another block of identical plain text, you would get identical ciphertext. It has the same problem as the electronic codebook mode we've seen before because there's no randomness. So that's one problem. But there's worse problems. This is called malleability, and it's closely related to the existential forgery attack, which we're going to play with in the projects. So if I have two ciphertexts, Y1 and Y2, that were made with X1 and X2 using the same key, then I can calculate the ciphertext for the product of those two plaintexts. If you multiply those two plaintexts together, the encrypted version is equal to multiplying the two ciphertexts together. So this means I can take ciphertext off, say, network traffic, one packet and another packet, and I can combine two ciphertexts and create another valid ciphertext message. Now, it doesn't mean I can create a ciphertext message with any arbitrary content, but it is a serious flaw in the system because a lot of people like to assume that if I send ciphertext to the server and it is valid, that proves I have the key. And that is not true for these simple systems. There are some valid ciphertext I can construct without knowing the key, and that is a flaw in the system. So to fix it, this is considered the best fix, although it is pretty mind-bogglingly complicated, which is this thing, optimal asymmetric encryption padding. You could just pad it by putting numbers at the end like we did with cipher block chaining, but here you use a padding algorithm, and the padding algorithm actually adds some random bits, and it's pretty complicated. The book doesn't go to it in much detail. It has a description I didn't bother with. I went to Wikipedia, and what I got out of this is why people don't use it much. This is pretty mind-bogglingly difficult. This is a Feistel scheme, which is how DES used to work. You feed in random data, you feed in key data, you scramble it in, you go through many stages here. It's surprisingly complicated, but anyway, this is designed to resist all the possible attacks if you use this fancy form of padding. Another much older, simpler system is PKCS number 1, version 1.5. This is commonly used by a lot of people. It was older, and a lot of people standardized on it, and they weren't motivated to figure out this nonsense and upgrade to it, even though it's supposedly more secure, which is the story with all forms of security. Everybody is using old stuff, and not often, even though there is a new, more complicated, supposedly more secure version, they just stick with the old thing until it's really badly broken. And so then the other thing you do with RSA is sign. It is important to understand that signatures are not equal to encryption, and this is what leads to a lot of problems, like some of the mistakes with padding oracles that we talked about before. There are people, as I said, who will assume that if you can send valid ciphertext to the server, that proves you have the key, and that is not the way the cryptography is designed. The purpose of encryption is to create confidentiality. It is not intended to authenticate you. Signatures are intended to make sure that the right person has signed the message, and it serves a different purpose. for example, the normal way you sign things, it is not a confidential message. You have a message X, and you attach a signature to the end of it, and then you transmit the signature and the plain text message through the channel. And the point of it is, you've signed it with X to the D mod N with your private key, D, and anybody who receives it can take your public key and the known plain text and the known ciphertext and make sure they match. And therefore, they can verify that that is your signature. That's the point of a signature. Yeah.
Is this how Apple signs their apps?
Yes, this is the digital signature standard. It's actually defined specifically using the RSA algorithm by law in the Digital Millennium Copyright Act in 1999, and that is what made commerce on the internet possible, because it made a digital signature have the same legal force as a pen and paper signature. And this is turning out to be one of the many problems of the internet, because it specifically refers to the RSA signature, and people are now getting worried that RSAs can be broken. And the alternative public key systems don't have the same legal force, or at least some people think they don't, and there will be arguments about this. Anyway, so of course, in practice, you don't want to sign the whole message. Typically, you just sign a hash. So you calculate a hash, then you sign the hash, and anybody who wants to verify takes the visible plain text, they calculate the hash, they raise it to the known public key, and if it matches, that means that this person who holds the private key signed it, and that it has not been altered since they signed it, or the hash wouldn't match and the signature wouldn't match. So that's the way the digital signature standard works. So this is textbook RSA signatures, where you just take the message to the D mod N. And if you do this without any of that padding, then you've got a problem. For example, I can forge signatures. For example, 0 to the D mod N is always 0, so I know the signature of 0 is 0, the signature of 1 is 1, the signature of n minus 1 is -1 to a power. It's either -1 or +1. So for these very simple messages, I can predict the signature, and I can predict even more signatures. This is a somewhat mind-boggling attack, but if I'm able to, suppose I have a message which the target would not willingly sign, and but I can generate another message that they will sign, and I can find this value R, so that the evil message is related by this calculation, R to the E mod M, then I can take the signature they give me, and I can calculate by taking S over R, the signature of that other message. And this is similar to that previous attack where you take two ciphertexts and multiply them together to create another valid ciphertext. You can take other signatures and combine them to generate the signature of a message that the original person did not sign, and that is what you're not supposed to have happening in the signature algorithm. You're not supposed to be able to generate the signature except by the original person who holds the private key signing the message. And so the solution, just like for encryption, is a better padding system, where you have a hash and you feed in some random data, and you have a padding algorithm so that you scramble it in a way so that it is not true that you can take two messages, just multiply them together and predict the answer. That's the game. You add some random bits and some fixed bits in the hashing process. This is like the salting a password before you encrypt it. This also, the randomness also means that if you have identical plain text, you're not going to get identical signatures, and that's another desirable property. So there's a simpler system that was around earlier called full domain hash signatures, where you just hash the message and sign it. That's it. Extremely simple and actually quite secure in practice. The only problem is there's no randomness in it, and that's going to make it vulnerable to fault attacks. In principle, the PSS is more secure than the full domain hash algorithm, but in practice, they're both pretty good. But the fundamental problem here is fault attacks. And fault attacks are probably the biggest flaw in RSA. There's a series of papers that came out that use hardware side channel attacks to break RSA. I've seen quite a few of them go by. Anyway, we'll get there. So there are libraries out there that implement RSA, and here's a few implementation notes. One problem is if you try to calculate things to high powers, if you multiply something, you want to take something to the 1/1,000,000th power, and you multiply it by itself 1,000,000 times, that becomes prohibitive. So what you have to do is square and multiply. So instead of trying to do 2 to the 10^24 multiplications, which is completely impossible, you create a library where you calculate the plain text, then the square, then the 4th power, 8th power, 16th power. And this is like a rainbow table. You now store all these things in memory, all these high powers, and then you just combine them. And this shortens the number of calculations very much. Now you can do 10^24 bit exponent with only 5,536 multiplications, because you just have to create these numbers and then combine them with a binary representation. If you have a 1 in this bit, you include this number. If you don't have a 1 in this bit, you skip this number and go on to the next one. So this is square and multiply trick makes it much faster. It makes it multiply as n log n instead of n squared, or 2 to the n or something ridiculous like that. So this is enormously valuable, but the problem is the whole thing that makes it fast makes it vulnerable to side channel attacks. Since you are now speeding it up by skipping all the multiplications you don't have to do, that means that the time consumed and the power consumed depends on the key. So the efficiency causes a leakage if you have a hardware attack where someone can monitor what your hardware is doing, or even a timing attack. So there are solutions, and one just came out this week from Microsoft. Microsoft Research put this thing out, and it is EverCrypt. This thing has been supposedly designed to resist a whole bunch of attacks, even in principle. It is supposedly proven from fundamental mathematical principles that EverCrypt will not fall to any of these side channel attacks, any kind of timing attacks. So libraries do exist that resist this, but they are complicated and many people don't bother using them. So here's another consideration we talked about before, I think. The reason why everybody pretty much uses the same E is because the normal situation is you have clients that are on cell phones and laptops and weak devices, and you have a server someplace with the private key that is a big server cluster on Amazon or something and has plenty of CPU power. So it is best to have a small e so your clients can do fast calculation on a weak device, and it is acceptable to have a large D so your server has to do more work. That is the normal sweet spot, so that's why most people choose a small e, and that means D is extremely large, like nearly as big as N. So you might imagine if you didn't do this, you just chose them at random, you'd have, if you had a 2048-bit key, you'd have a 1024-bit E and a 1024-bit D, and both of the calculations would be very onerous. But by choosing a very small e, then D is almost as big as N, and that makes the calculation on the server bigger, but on the client faster. The Chinese remainder theorem makes all this 4 times faster. It turns out that when you're going to try to do x to the e mod n, this mod n is what makes it very expensive, because n is an extremely large number, like 2048 bits. And it turns out you can, since n is the product of p and q, you can express this as 2 calculations, 1 mod p and 1 mod q. And not only that, these numbers don't vary, so you can calculate this once in advance and then reuse it over and over. So this makes RSA 4 times faster. It does, however, make it more vulnerable to fault injections. And so here's how things can go wrong. The main one is fault injection. This is a side channel attack. If you modify the hardware, it can cause it to drop a bit at some point during the calculation. Those bits that does not create a random change, it creates a predictable change, and that can leak out information about the key. And one paper I read about 10 years ago showed that if you lower the power supply in a processor using, I think, OpenSSH, and you only encrypt 1,000 times, so that 100 encryptions dropped 1 bit, that's enough to completely determine a 1024-bit key. And so that's a problem. And the cure here is to use non-deterministic systems like PSS that add something random every time, because that means even if you encrypt the same data 1,000 times, you'll get 1,000 different answers, and you can't tell which ones of them included the error. So that breaks the system. All right. And there was another attack that was pretty esoteric, and I didn't bother with it. I think what I'm going to do is I'm just going to pause to share for a minute and put my things in Kahoot, because it'll only take a minute. And then we can do the Kahoots, without which it's less fun. So I'm going to pause the video recording, and I'll put up the Kahoots, and it won't take long.